welcome to Programming for Fun with Scratch. This is episode 4. My name is Dee Thelza. I'm a digital services technician with the Richmond Public Library. Today we're going to be talking about simulation games, and we'll look at a bunch of examples, and then we'll also discuss a little bit about making custom blocks in Scratch. So let's go ahead and start taking a look at that. So Scratch has several pages on its wiki about simulations. So this is its simulation projects page, and all of these pages and projects that I show you will have links in the description to this video. So one of the difficulties about talking about simulations is you can mean so very much by it. So you can see here there are life simulations, vehicle simulators, physics simulations, math simulations, operating system simulations, chatbots, comment simulations. And that's really only just scratching the surface. If we look then at, there's a simulator games studio. It has more, and then there's also a studio for physics simulations and animations. And again, this only scratched the surface. There are things like SimCity, SimEarth, SimRollerCoaster, The Sims. All of these are different types of simulations, and they're just a very small subset of the various kinds of simulations that you can do. So that makes it a little complicated about where to start. So what I'm going to do is start with one of the simplest simulations we can do. We're going to simulate an ant, and not even a real ant. We're going to simulate something called Langton's ant. Now, Langton's ant is it's a cellular automata. The most famous of the cellular automata is Conway's Game of Life, which we may look at in a future episode. Langton's ant, so a cellular automata is on a grid of squares called cells, and in the Langton's ant, each of the cells is either black or white, on or off. And the rules of Langton's ant are very, very similar. Let's try and zoom in a little bit on this so you can read it. But the ant is on a square. It can go left, right, up, down, and when it moves, if it's on a white square, it turns 90 degrees clockwise, so it turns to the right, and flips the color of the square, so now that square will be black, and then it moves forward 1 unit, 1 square. At a black square, it turns to the left, 90 degrees counterclockwise, also flips the color of the square, so that square is now white, and moves forward 1 unit. And you can see it doing that in the right-hand side, and it seems to be fairly chaotic what it's doing. It's interesting because it goes through several stages. If you start on a completely white grid, it's very simple, sometimes fairly symmetric, the moves at the beginning. Then it gets very chaotic, and then after around 10,000 steps, it starts building a highway. And you can see in the upper right here, there's a bunch of chaos, and then the highway is going off and down to the lower right. And it will pretty much always do that. You can create Langton's ant on a grid that is not all white, and then you can get different effects. We will actually experiment with what happens when we have multiple Langton's ant, once we get the basics of one working. And of course, it's been extended to have multiple colors, and there are many, many different ways you can go. And sometimes those are called termites, which are Langton's ant with more rules. Here's extensions to multiple ants, which is what we're going to be doing, and then links to other cellular automata. Okay, so this is the Wikipedia page on Langton's ant. Let's take a look at our first project. So the temptation with Langton's ant is, at least for me, that the screen is already a grid of pixels. In Scratch, they are virtual pixels because they can be scaled up and down. So they don't correspond to real pixels on the physical monitor that we're looking at, but we can treat them as if they did. And so there's already a grid there. Unfortunately, things like touching color don't work very well if we're mapping down to the pixel level because it checks adjacent pixels as well. So our first ant, and make this a little bigger. So hopefully you can see these blocks now. So we have just one event when the green flag is clicked. We're going to erase everything that we've done previously and set iterations to 0. Iterations is simply a utility for us, so we can see how many times we've taken a step, how many times the ant has moved. And we'll probably drop that later, but I wanted to show you that in this beginning script just so that we can see a counter and know when to expect chaos and order to start emerging. We'll start at the very center, which in Scratch is 0, 0. That's 0, negative 0, which is not necessary. So just 0, 0. And we will point in direction negative 90. This will align our ant with the one on the Wikipedia page, so that the image that we create should match the one on the Wikipedia page. And then we go into a forever loop, as is common in most games. So we're going to loop forever. On each step, we will count up our iterations. So we'll count a step. And then we have an if-else is the main piece of this. So if we're touching black, switch to white. And what we're doing is we're using costumes. We have 3 costumes. We have a red costume so you can see where the ant is, and a black costume to stamp black, and a white costume, which you can't really see here, to stamp white. And those costumes are, if you look carefully, it shows you in the left how many pixels they are. So this is 4 by 4. They are all 4 by 4. And I'll tell you in a moment why. Well, and where you can read the comments. So we'll switch our costume. If we're on black, we switch the costume to white. If we're on white, we switch it to black. We turn left to right, depending what color we're on, and then we stamp the color. So stamp is from an extension, the pen extension, which you can see if you go down all the way down to the lower left-hand corner on extensions. There are a number of extensions we can use, and pen is the one we're using here. Pen gives you a bunch of drawing tools, so you can say pen up and pen down, change pen color and width, and then if the pen is down, wherever your sprite moves, it will draw a trail along there. So that you can create some really cool effects. We're mainly using clear, erase all, and stamp. So we're not actually using the pen itself, just a couple blocks from it. All right, so stamp will create a print of our sprite on the screen, on the stage, and then erase all will erase the stage back to what it was. Then we switch costume back to red so we can see the ant and move. So we're not in Langton's ant. It moves 1 step. We're moving 5 steps, which is 1 step for us because the costume is 4 pixels, and then we need to add 1 extra pixel so these touching color doesn't pick up the wrong thing. Otherwise, because it does check adjacent pixels, not just the pixels we're on, it would always register white, basically. Or it would register black when we don't want it to. So we move 5 steps. So 4 pixels of the sprite plus 1. This is optional. It just says when we get to the edge of the screen, so there are 240 pixels in X in either direction from 0, so negative 240 or positive 240. So if we're greater than 239 in the absolute, so absolute just strips off the negative, so that'll get us in either direction. And then we do the same for Y. There are 180 pixels in either direction, so it's greater than 179 absolute, so it goes in either direction. If we get to that, we stop the simulation altogether. Okay? So that is how we get out of that infinite loop. Let's try it and see. So now we see the ant, and it does seem fairly random what it's doing, even though we know it's just those 2 rules. It's either moving to the left or right, and then changing the pixel it's on. And now we get some kind of pattern here. It looks actually fairly regular. And it keeps going and going. And we're not going to watch it every time because we actually are going through 7 different scripts today. You can see the iterations going up. We haven't even gotten to 1,000 yet. I am going to go over here. Under Edit, we have Turn on Turbo Mode. And now, that should speed it up. And actually, we're going to see some differences once we do different implementations of this in how well that turbo mode works. But here, I will probably just speed up the video so that you can see it, because the turbo mode doesn't do a lot. And the reason why it doesn't do a lot is, I believe, because that if touching color is a very expensive, meaning slow, operation. And so when we find an alternative way of checking the color, which we will do in a subsequent script, turbo mode does speed it up dramatically. It's very fast. Here it's a little bit faster, but not by much. And there we go. So it's interesting that out of such simple rules that we can get such interesting behavior, both very stable looking patterns like the lines and the loops, almost circles, and then chaos, and then it falls into this regular kind of highway building, which will continue on an infinite grid, will continue on forever. And it always falls into that. And it will, because we're starting with the same rules every time, it's completely deterministic. On a pure white grid, it's always going to build exactly this pattern. So, but that's part of the fun of building simulation games, is to see this kind of emergent behavior. And what we're going to do now is we're going to look at different ways we can tweak this simulation to get some interesting effects, and just to learn a little bit more about Scratch as we go. All right, so the second one, dive into. All right, so the second script, Langton's Ant 2, if you're following along with the links. What's different here is mainly that we have made our grid a little smaller. We're trying to get it down to that pixel level to see what it's going to, just to see what it's going to look like at the pixel level. So this is a little closer. This is going to be steps of 3. So our costume now is 2 pixels in size. We've still got the same red, black, and white, but now they are half the size as before, and then we still take one extra step so that we can use touching color. Oops. And so here you can see it is it's still pretty big compared to individual pixels, and we've still got a gap which makes each square fairly distinct. And I'm not going to run through all the way on this one, but I wanted to show you what that looks like as we make it a little bit smaller. One reason to make it smaller is then we can fit more ants on the screen to see how they interact, because while one ant is perfectly predictable what it's going to do, once you've seen it once, it's going to make the same pattern over and over. Multiple ants, while still completely deterministic, ants placed in the same positions and facing the same directions will create the same pattern over and over. It's very difficult for people to predict what those are going to do. And so when we add more ants, it creates even more complex emergent behavior. So that is Langton's Ant 2. That's really not a big change from 1. Let's look at 3. Now in 3 we are trying to get it down to the pixel level. And so we have added we're still moving 2 steps. We actually had to change our costumes. So our costumes are still red, black, and white, but they were vectors before. And so if you remember the difference between vectors and bitmaps, a bitmap tells the browser what color to put at every pixel for the sprite, and a vector tells it kind of using math to say, from here to here, draw this color. From there to there, draw this color. So vectors are interesting because you can scale them up and they don't get blocky, and you can scale them down, and they're very nice for certain effects. Bitmaps, if you scale them up, they'll get more and more pixelated because it is saying for each pixel what to do. And so when you scale that up, it doesn't go as smoothly as a vector, which is more instructions for how to draw a shape rather than the actual pixels of the shape. I hope that's understandable. In Scratch, it would not draw. The stamp actually had no effect on a 1x1, a 1 pixel vector sprite or costume. So by changing it to use bitmap, it actually would draw. So that's why we had to make that change. Each of these, as I push things, I learn a little bit more about Scratch. So hopefully I can pass those along to you. We still have the stop when you get to the edge. That's the same. Most of this is still the same. So we have just reduced the size of the sprite down to 1 pixel now. We still have to take an extra step to be able to use touching color. This is what that looks like, and hopefully you can see that's actually wrong. Huh. Interesting. I have tested all of these, but maybe I messed something up here. Huh. Okay. I'm not sure why that is broken. It definitely is. That is not the Langton's ant pattern. It may still be related to the fact that Scratch gets a little finicky when we get down to the pixel level. I thought I had all these working. Anyways, moving on, let's look at Langton's ant 4, which is where things start to get a little more interesting. So now we're not going to use touching color to organize our drawing code. Instead, we're going to keep track of every pixel on the screen ourselves. So we're still stamping, we're still start with an erase all, we start at 0, 0, turn in the same direction. That part is all the same. But now we have position, and position is, if we go to variables, you can make a list. And position is a list, and it is a list that is has an entry in it for every pixel on the screen. So there are 480 pixels in a row and 360 rows. So we multiply those numbers, and that's how long we have to make our array. And we go through and repeat that many times and adding white to the array at every position. So, or position is the array, but we add white that many times. So we have said, yes, start the screen completely white. And now it's a little more complicated, not a whole lot, but a little more complicated to go through our forever loop. So we need to have a couple of additional variables. We have an index variable, which is what our coordinate is in that array. And we have a touching block variable to say, are we touching black, or touching black variable to determine if the current pixel we're on is white or black. Okay, and this math here, this y position plus 180 times 480, or plus times x position plus 240. All right, what's all that? So this is converting, because we x and y, the pixel grid that we're on is two-dimensional, and our array is one-dimensional. So we need to be able to convert. We have an item in the array for every pixel on the screen, but we have to be able to convert between the x and y coordinates to the index coordinate of the array. We also can't just do that as simply as in some languages, because in Scratch 0, 0 is at the center, so our x and y go negative. Whereas in most languages, most programming environments, 0, 0 is at the top left, and both x and y are always positive. So what we have to do is convert that. So we add 180 to y position to make it positive and increasing, and we add 240 to x to make it always positive. So now what we can multiply our y position by maximum of x. So because each y contains 480 pixels, right? Each row, and we have then 360 rows. So if we multiply the row by how many pixels it can hold, and then add the x position once we've made it positive, then we can get a unique index into our array. And so this converts from the XY grid to a single number, from two numbers into one single number that exactly matches back and forth between the flat index, the one-dimensional index, and the two-dimensional grid. So now that we have an index, we can say item index of position, which is our array, and that's going to go into this value touching black. So because everything in the array is white when we start out, this will now have the value white, just the string. So now, if that touching black equals the string black, which it won't at first, but it will soon, because we're going to start changing some of the items in the array, then replace that index with the string white. Not that index, but the item in position at that index, at the current index. Switch costume to white and turn 90 degrees. Otherwise, replace the item of position at the index with the word black, switch the costume to black, turn clockwise 90 degrees, and then this part is the same. We stamp the current costume, switch costume back to red so we can see the ant. And now we can move one step because we're not relying on that kind of fuzzy color matching if touching color. It takes a few more steps to determine our color from the array, but now we can actually get down to the pixel level. So we have a 1 pixel costume again, and again it has to be in bitmap form, or stamp won't work, won't do anything. And again, at the end, when we run into the edge, we just stop the simulation. So now we can actually have single pixels. And that may be kind of hard for you to see. What I'm going to do is the other effect of using an array instead of if touching color is pretty neat, because now if we go up under edit and say turn on turbo mode, turbo mode gets really, really fast. And so we get to see just how slow it is to check if we're touching the color by how fast it is when we route around that. And we're going to use that now in future episodes when we revisit things like platforming games. We'll see ways that we can get around using if touching sprite or if touching color and do our own collision detection. We'll have to write a little bit more code, but we will get both better performance and much more powerful collision detection, because now we can say, is the head of my sprite touching a platform, or the feet of the sprite touching a platform? And that lets us do things like hit a brick with our head versus landing on it and stopping the gravity from making us fall any further. So that's cool. So adding an array, we have to have a couple extra, both the array and a couple of extra variables. But, and now we also have to say, in addition to changing the color on the screen, we have to change the color in the array. So we can't just have one thing. Before, the screen was tracking all of our state. We just check the color that we're standing on, and then we know what to do. Now we have to check the color. We have to check the color in the array to tell us what to do to what we're standing on. So the state is in the array, and then we just start drawing that on the screen. It's a little more work, but you can see it makes it much faster, and we can get down to the single pixel level. All right, let's take a look at Langton's and 5. Now we've broken things up a little bit. We have this erase all just to start things off cleanly. So now we've broken up the code, now that we can get down to the single pixel. So we have, when the green flag is clicked, again we erase all and delete all of position. So we're starting off with a clean array. We initialize our array to all be white, just as we've done in the previous one. But now we repeat 10 and create clones of myself. So now, instead of there being one ant, now we have 10 ants, and we can have more or less by changing this repeat number. So each ant, once it's cloned, is going to have this when I start as clone. And these clones are really kind of interesting. So you can take one sprite and make lots and lots of copies of it. When we were stamping our sprite, we weren't really creating a copy of the sprite. We were creating a copy, like a picture of the sprite on the stage. Now we're creating a standalone sprite that has its own behavior and can interact with things and run its own scripts. And so each of the copies of this sprite now are going to be running this script that starts off when I start as a clone. And so you have, under the control blocks, you have when I start as a clone, create clone of myself, and delete this clone are the clone blocks. And you can do some really powerful things with this, especially when you want lots and lots of sprites on the screen. Like if you have missiles or asteroids or all sorts of different things where you might want to have more than one of the same sprite. You could use clones. All right, so each clone, instead of starting at 0, 0, now that we have multiple, we're going to have multiple ants at once, we start at a random position. And random position is a great block that just picks anywhere in the XY plane and it puts us there. And then we point in direction. Now we don't want to point in any random direction, 360 degrees or whatever. So we are picking a random from, well, this should be 0 to 3, up to 10, and then multiplying by 90 degrees. So we should be facing right, left, up, or down. And then our forever loop is very similar to what we just had. So we have to get our index, we get touching black. If touching black equals black, then update the index to be white, set our costume to be white, and turn counterclockwise. Otherwise, set the array at this position to be black, switch our costume to black, turn clockwise, 90 degrees. Stamp, switch our costume to red so we can see the ant, and move one step. So this is the same as Langton's ant 4, just that now that we have multiple ants. And this part has changed because when we hit the edge of the screen, we don't want to stop the entire simulation. We just remove this clone, this ant. So, but we leave the rest of them still running. I am going to go ahead and turn on turbo mode. And let's make it big. And hopefully you can see what happens here. So now we've got lots of ants going. They're going crazy. They're building their highways, but now their highways collide with each other. And we get interesting things like this down in the lower center where it keeps going. We have two ants that have collided, and essentially one of them is erasing parts of the first one. They're each as part of the collision, they go and erase part of the other and then redo it. And it's going to create a loop that goes on forever. So normally the ants are always going to create, left to their own devices, they're always going to create a highway and go off to infinity. But there are cases where you have two ants that collide and can create this infinite loop where they are undoing and redoing the same bits over and over forever. So that's kind of cool. This one is also, it's going to be different every time we run it. So because we're going to random positions and point in random directions, so we see a lot of these colliding, and we may get some interesting effects where they collide and don't create an infinite loop, but just send off highways in different directions. So you get this kind of really big cluster here of sometimes it gets into a loop, and sometimes it just diverts the highways. It may be chaotic for a while, and then the highways emerge anyways. We can also play around with more than 10. So what happens if we have 20 ants? And with you can see with turbo mode, because we have this this array that we're using, and they're all using the same array. That's the important part. Is it's still, even with 20 ants going, it's still really fast. And you can see sometimes it gets chaotic as they collide into each other, but then eventually it resumes building the highway. And sometimes it just loops forever. So these two are very close to each other, and they're just erasing each other and rewriting. And then here are two that were further apart, but they're doing that same thing. So that's fun. You can play around a lot with this one, where you just try it again and again and see what things emerge from the having them in random positions. Moving on now to Langton's Ant 6. What has changed here is we don't have a loop to create. We're just creating two, and we're going to actually play around with that whole idea of two ants facing each other and what effects emerge. So we have two sliders. So one of the ants we're going to draw at 0, 0. It's always going to be fixed. It's always going to be facing in direction 0. The other one is always going to be facing 180 degrees opposite, so they face each other basically. But we have some positioning that we can do. By changing these sliders, we will change the starting position of the second ant so that we can see what happens when the two of them collide from different positions. So I'm going to turn on turbo mode because that will help us see what's going on. And then we're going to big. So now if I just do 0, 0, they just collide right away, but they still go off in either direction. So now I'm going to try, let's try 10 and 11. There we get a stable loop. So now they're colliding and erasing each other and rewriting each other themselves. So, and now if we try 20 and 21, I think we also get something. And this is another one that it's a lot of fun to play around with, and you may get some surprising results now and then. I had one that I did not write down the coordinates that was quite interesting. So now we get bigger patterns, bigger loops, but it's still the two are colliding and erasing each other and rewriting each other. And I think that you get some artifacts, some little specks, which I think are just the sprites aren't exactly 1 pixel. I think there's a little bit of or Scratch is just not. Basically, when we get down to the pixel level in Scratch, it's a little tricky to make it happen completely cleanly. But it's 100% accurate in the array, so we get the right behavior. Just sometimes we get these little specks and artifacts. So this we can try any numbers we want. The X and Y only change what the starting positions are of the starting position of the lower left-hand one. So this one is interesting because they sent highways out, then collide, have some more chaos, and then send highways out again. And you'll see that a lot in different ways. So if we make them both 29, now the highways go off in a completely different direction. So we have like highways collide, sending off other highways that collide again, and then sending off highways finally to infinity, but in a different direction. And we can just pick random ones and see what happens. So this one looked like it might go into a loop, but it didn't quite. And maybe if we do just one pixel change, now it's a loop, right? So 13 and 8 is a loop, but 13 and 9 is not. So it's very sensitive to what positions you started at. 10 and 9 is a loop. 10 and 11 is a loop. 10 and 10 is not. And this one's interesting because it goes off in different directions. Now, how can that be? Because they both start at the same point. It's all predictable, and they're just running into each other. How can they go off in different directions? And that's because they're both using the same array. Now, there are implementations where if two ants both land on a black pixel, they will turn it white and go off in their own ways. And you would not get this. But in Scratch, when two of the ants land on the same pixel, one of them will change it. So if it's a black pixel and one ant lands on it, it will change it white. And then the other ant will change it black. And so you can get this kind of unpredictable behavior where they go off in different directions because it happens sequentially. So Scratch doesn't do processing simultaneously of the sprites. It's always going to be sequential. So one sprite is going to act, then the other. And because they're all operating on the same array, they can mess with each other this way, which is also kind of fun to see, but something to be aware of in your own code. All right, so this is something you can play around with all you like. We have, I think, one more. All right. So now this one is similar, but what are we doing now? We made the pixel. We're going away from pixels and back to larger sprites so we can see what's going on a little better. Make it turbo. So now we're mixing the code from the earlier ones where we have the costumes and we move 3 steps because we have a 2 pixel sprite now, but with the indexing. So our indexing is a little different. We had to change the rules because we're not going through every single pixel of the screen. And again, we have one sprite in a fixed place and the other sprite that we can manipulate the starting position of. So I think I turned on turbo mode. Yep. And now we're going to go into big. And so now you can see what's going on a little better. I wanted to get down to the pixel level so we could have lots of sprites, but now that we're just playing around with 2 sprites, it seemed better to have just bigger pixels, so you can see what's going on when they collide. And also, the bigger pixels seem to be cleaner. We don't have the same kind of artifacts that we do when we're drawing single pixel sprites or costumes. We don't have the little what was it called? Noise or cruft. So with two ants, we can have nice big pixels. Otherwise, this is the same code. We could go in and create more than 2 ants using the bigger pixels as well if we wanted. And then for the last one here, what this is, I think this is the same thing. No. 3 steps. Did I just have this open twice? Oh, that's an interesting one. They really go and they don't just rewrite each other, but they cause some chaos with each other, but then they undo it all and go back to nothing and start again. Oh, I like that one. And playing around with the different numbers, you can come up with some really different effects. And it can be just one number different. Sometimes will create a completely different. See, this one is not stable, and they go off in their own directions. Such a simple rule. Move, go to the left or go to the right. Change the color of the pixel unit. It's all this is, and you get all of this amazing complexity. We'll revisit simulators again in a later episode and do something a little more complex than this, but I wanted to start us off with something where we have a really, really simple rule, and then we get all this wonderful emergent complexity from it. So that's everything for simulating Langton's ant. But now we do want to talk a little bit about custom blocks. Now we've used custom blocks before in our scripts, but we haven't talked about them a lot and what they do. So every block in Scratch has an effect when it runs, and we can create our own blocks, our own command blocks. We can't create these hat blocks that are for events, and we can't create reporter blocks that return a value, but we can create command blocks, which is a good start. So let's take a look at what would we do to simplify our code here by creating some blocks. And the main reason to create your own blocks is if you have complex code that you want to simplify. So you can create a block simply to give something a name. So here, let's see, we are setting this index based on this fairly complicated rule, this math. So we could say have a block called setIndex that does this, and we don't necessarily have to see what all of this complexity is. So let's take a look at what that would be. So make a block, setIndex, and it's just using our own internal variables. So just want it to do that. Whatever code we have underneath that defined set index is what's going to be called when we use the set index block. Now we'll put that whole thing back, and we should have exactly the same behavior. There we go. We can also the most useful place for a block is when you have repetitive blocks. Like here we have very similar code and a bunch of it. So we could have a block that basically does this whole if-else. It would be tricky to have a block that does these two different things without and actually make it less code. Although we could have it with the same amount of code that it is now, but by dividing it out into blocks, our main loop is cleaner. So let's try that. So here we're going to make a block that just does this if touching black part. So what do we want to call that? So we are replacing an item, we're switching costumes, returning 90 degrees. So let's see. So we'll make it white. Make it say step white. Now we could pass in a variable, an information using either Boolean or number or text, or we can also add more labels like in between if we have multiple inputs. But for now, I actually tried that, and it didn't really simplify the code much, because I still had to do all of these ifs, and actually I had to do the check multiple times, so that didn't help a whole lot. So, but this way, cleaning up our main loop is still a win. And now we'll make a step black. Naming things is important. It's hard. It's hard to come up with good names for things in your programs, but it can make it a lot easier to understand what's going on if you choose names well. Alright, so now if it's black, step white, otherwise step black. That sounds pretty good. Let's say check edge for this. We have to make sure that when we define our block, that we still use that block that we've created in our main script where we were, from everything we replace. Otherwise, we're going to break things. And now we can even make a stamp for this, or a block for this. What this can do also is, because we have a lot more code to check in the array, we can make it still simplify, streamline how it looks in our loop, so it doesn't look like a lot more code. We kind of hide that complexity off in custom blocks. So I'm going to make a block now to, so we said step left, step right. Maybe now we actually take a step. So we can have custom blocks in custom blocks. Alright, so here we are. Now this is pretty clear. We loop forever. We set the index. We could even set our touching block as a custom block. But if we are touching black, if touching black equals black, step white, otherwise step black, and then take a step. So now we can more easily read what's going on in this main loop. It's not getting down into the weeds of what each of these things what needs to happen for each of these. We could clean up this, but because we only run through it once, I'm not as worried about that. But we could have like initialize, especially if we were going to, rather than just completely starting fresh, but if we wanted to keep going like in a game with multiple levels, we would want to break all of our initialization code off into an initialize block, because we might initialize differently for different levels. So we might have initialize level 1, initialize level 2, something like that. Here, because we're just doing this very simple simulation, our initialization code is just erase everything and start over. Now, the other thing I wanted to see is what happens if I turn off turbo mode. But we can go into these blocks, edit them, and we can check run without screen refresh. Now, turbo mode, as far as I can tell, is both doing this run without screen refresh and also taking the limit off how fast it calls each iteration of repeat forever. So repeat forever essentially happens once per frame of animation usually. So it's not going to usually run more than 30 times a second. I think when we go into turbo mode, it just runs as fast as it can. Now we saw in the earlier demos, the earlier scripts, that turbo mode didn't really do much when we were using if touching color. And I think that's just, it takes a lot of processing to tell if we're touching the color. And that slowed the whole thing down so that there wasn't much speed up to gain from turbo mode. But when we switched to using our array, we gained a lot from turbo mode. Now I've turned turbo mode off. What I'm curious about is if we make these custom blocks not update the screen. So we've gone in, we've edited them to say run without screen refresh. Do we get some of that same speed up? And I'm thinking not really. I think maybe this particular script, there's just not as much to gain by not refreshing the screen. I think also we're still limited to probably 30 frames per second. So if you have a script that seems to be running very slowly, probably dropping below that 30 frames per second, and it is doing a lot of drawing on the screen that you don't need to have in between frames, you might be able to use custom blocks and turn off that, check that run without screen refresh. I have had some scripts where that sped things up quite a bit, and others where it really didn't have that much effect. And sometimes it'll actually break what you want because you actually need that screen refresh for what you're doing. So it's something to play around with. There's lots you can do with custom blocks, but mainly it's about organizing your code. This is the same script that we had before. It's doing, it's not doing anything different. It is just doing it with a little bit more organization. And that's for our benefit. That's so we can read it. And occasionally we can use it to speed up our code by checking run without screen refresh. But mainly it's a way to remove repetitive blocks. If we're doing the exact same code over and over again, move that into a custom block and just use that. And or if you have some code that it isn't entirely clear what it's doing, move it into a custom block so you can give it a name. Or if your script is just getting too long and it's just hard to read through and understand what all the different parts do, move bits of it into custom blocks so that the flow of it is clearer, easier to read, easier to understand. That's really the goal of custom blocks is those uses. Okay, I believe that is it for today. So I hope that's been fun. I hope you've learned a little bit more about writing simulators, and we will we'll pick up with more complex simulators in the future. And next week, I think we're going to do, or next week, 2 weeks from now, we're going to do an arena game, and we'll look at some of the things we can do for that. Until then, thanks for coming by. I hope this has been fun, and have a great time playing around with some of these examples. Bye-bye.